Increasing concerns regarding the presence of elevated indoor radon have caused many individuals and building owners to test their homes and workplaces for radon, and if found to be elevated, have taken action to reduce radon exposures. This is certainly true for schools, where a safe environment for children and staff is a high priority. Often repairs can be implemented by maintenance staff. More complex situations may require the use of certified radon professionals. But regardless of the approach, radon reduction technology is well known and, if applied logically, will result in healthy environments for students and staff. This program, sponsored by the North Dakota Department of Environmental Quality, is designed to enable school maintenance personnel to implement a radon reduction program. Hi, I'm Doug Clotter, and in this program we will help you interpret results of a radon survey and help you determine if you really do have a problem. Learn how radon enters a building so we can focus on effective methods to reduce it. And most importantly, how to reduce radon, often with simple repairs. There is also a companion video to this one that describes results of a radon investigation of a school in North Dakota, so you may want to check that out after you finish this program. So let's get started. To begin with, radon is a naturally occurring element that can be found anywhere in the world, with some locations having higher potential than others, due to variances in geology as well as climate. When radon enters a building, regardless of the mechanism, it can increase the potential for lung cancer if occupants are exposed for long periods of time. The U.S. EPA and the U.S. Surgeon General recommend that long-term exposures not exceed 4 picocuries per liter. Getting below 4 picocuries per liter is the target for your efforts. In fact, proper mitigation will often reduce it to less than 2 picocuries. The most common source of radon is from the geology under a building. That is true for any building, home, office, church, or school, regardless of its age or proximity to any landfills or cleanup sites. In other words, any building can have a radon concern, and the only way to know is to test the building. Being a gas that is generated in the soil, it can easily pass through openings in the foundation where it contacts the soil. Large openings are not required, which is why simply sealing apparent foundation openings is not effective. When a source of radon exists under a building, soil gases will enter through foundation openings due to vacuums within the building that pull it in through these small openings. These building vacuums can be caused by natural thermostat effect, but even more so in the case of schools, the building's heating, ventilating, air conditioning system, or HVAC systems, can create large negative pressures that will pull radon in from the soil. Radon can also enter if the underlying soil is under pressure due to environmental conditions such as wind and if the subgrade is porous. However, the primary entry mechanism for radon entry is the negative pressure or vacuum within the building itself, and anything that changes the interior air pressure will affect radon entry, either increasing it or decreasing it. This leads to a discussion of the building's HVAC system. Modern schools have systems for heating and or air conditioning the building. These may be rooftop units that serve multiple rooms with air distributed through balanced ductwork. Alternatively, there may be individualized unit ventilators, each serving an individual room. In either case, these are set up to recirculate interior air to heat it or cool it. They are also set up to bring in fresh outdoor air when the building is occupied. This provides fresh air into the building for occupant comfort and to reduce accumulation of carbon dioxide and other human effluents. In the case of centralized air handlers, typically roof-mounted, there will be a grill that allows outdoor air in. There will also be a damper for controlling the amount of outdoor air that is provided when the building is occupied, or shutting it off completely during unoccupied hours. The provision of outdoor air is typically controlled by an energy management system. There will also be a filter to remove particulates from the air introduced to the building, as well as a dehumidification coil to reduce humidity of the supplied air. These same elements exist within unit ventilators. There is an outdoor grill with a damper as well as a filter contained within each unit. But regardless of the type of unit, the provision of outdoor air can greatly influence the vacuums within a building and hence the entry of radon. Providing outdoor air can do two things. One, it will dilute radon. And two, it can also create a positive pressure inside the room or building that will resist the entry of radon. Here's an example of an hourly radon measurement taken in a school where fresh outdoor air was only provided during occupied hours. One can clearly see that radon levels were greatly reduced to below the EPA guidance of 4 picocuries per liter when the outdoor air was provided, even though the overall average for a typical test period of 2 days was above 4 picocuries per liter. Unfortunately, there may be situations where the fresh air makeup is not being provided as the HVAC system was originally designed. This may be due to air intakes being intentionally blocked to reduce energy costs for heating or cooling the outdoor air that's provided. It may also be where the damper motors that control the air intake have broken or the linkages even disabled. The amount of outdoor air can also be reduced if the filters have not been changed or the dehumidification coils have not been cleaned. In these cases, even if the outdoor air damper is open, insufficient air may be provided. It is always good to verify air is actually flowing at the design flow rate by either measuring it or using a smoke bottle to verify there's at least some air being introduced. Here is an example of an outdoor air intake on a unit ventilator where access to the filters from outside had been blocked when the brick was repointed. This condition prevented maintenance from changing filters, which over the years had become completely blocked and not allowing any outdoor air into the classrooms. These systems typically have temperature sensors and controls that will shut off extremely cold outdoor air. This is a safety feature to prevent freezing and the damage to coils. Should these sensors fail or the signal lines to them, whether it be electric or pneumatic, fail, the damper will close in a fail-safe position, which would be in the closed position, stopping all outdoor air. So maintenance of these controls and ensuring they have not failed closed is important for maintaining good air quality and low radon levels. In the case of a central air handler, air is drawn from multiple rooms and returned to the air handler to be heated or cooled. The air is then supplied back to the same rooms via a separate system of ductwork. Since outdoor air is also introduced in the air handler via its return duct, the amount of air supplied to a room should be greater than that which is withdrawn. This positively pressurizes the room, which would retard the entry of radon into that room. Of course, that assumes that the balancing dampers on the ductwork have been properly set and maintained in their balanced position. However, dampers can be changed, or more often, an occupant may close off a supply grill if the air blowing on them may be distracting. The effect of closing a supply grill is to make that particular room go under negative pressure, since air is still being taken out of the room with less air being supplied. This negative pressure condition can cause radon to enter that particular room, but not adjacent rooms where the supply has not been restricted. Another example of unbalancing is when remodeling occurs and where a partition wall is installed in an existing classroom or perhaps a movable room partition is used. If both supply and return air is not provided on both sides of the separation, the side with the return air can go under negative pressure and cause high radon levels on that side. The effect of unbalanced airflow is why one often sees significant room-to-room variations in radon levels. It is the reason why in a school or office building it is important to test every occupied room in contact with the soil or directly above a crawl space. A situation that is specific to unit ventilators is that the lower portion of the cabinet is the return air plenum where air is pulled from the room and reheated. There is a significant vacuum within this lower portion of the cabinet. It is also where heating pipes can enter from beneath the slab or from a utility tunnel located under the unit ventilators. If these floor penetrations are not sealed, the unit ventilator can literally mine radon through the gaps around the pipes and introduce it into the room. These penetrations should be well sealed, and the degree to which they are sealed can also cause room-to-room variations in radon levels. Importation of radon via an air handler can also occur when the ceiling is used as the return air plenum. This is often done to reduce cost of installing ductwork to separately run air to the forced air unit. This practice causes the entire ceiling area to be under significant negative pressure. If there are pathways to the soil, such as behind stud walls or demising walls, this can draw radon from the soil and introduce it in the air handler, where it is then distributed throughout the entire building. Of course, missing ceiling tiles in such a system can also create negative pressures in a given room. There may also be rooms that are exhaust only. An example of this might be a room with a kiln for a pottery class, where hot air is exhausted to the outdoors, or perhaps kitchen hoods in the food preparation area. In these cases, there should be a means for providing additional outdoor air to replace the exhausted air when the exhaust fans are switched on. If not, this individual room, as well as other rooms communicating with it, can have high radon levels. One last aspect of an HVAC system controlled by an energy management system is that not only is the fresh air makeup reduced or shut off at night, fresh air makeup is also shut off on the weekends. The conditions that exist during weekends are not what students and staff are exposed to, and the results of a radon test conducted over a weekend, quite frankly, is meaningless. Unfortunately, school personnel and even radon professionals have conducted short-term tests over weekends to minimize disruptions. However attractive that may be, avoid testing over weekends or long holidays, as it may cause you to fix a problem that doesn't exist. Radon testing is unobtrusive and should be conducted during the school week. So now that we have talked about what can cause radon to enter and what can prevent it, I think you're probably getting an idea as to what you want to go check out. But before you do, let's start from the beginning of the entire process, beginning after you receive the results of an initial short-term 2 to 3 day test survey. First, let's verify that the tests were conducted during the school week rather than the weekend, and during a time of year when radon levels will typically be the highest, which would be wintertime in northern latitudes. Then verify they were set out for a minimum 2-day period. It could be a few days more, provided the test period did not go into the weekend. Also, at least 10% of the room should have had duplicate side-by-side devices deployed where you can compare the results to see if the results agree with each other. And also 5% of the rooms that have had undeployed devices called blanks that are analyzed with reports of results being at the lower level of detection, which is typically less than 1 picocurie per liter. Note that the radon professional who conducted the test should have performed an assessment of these quality control measures, so look for it. If it's not there, ask for it. So if everything checks out and you have confidence in the test results, pull out a fire escape plan and transfer the results to the floor plan. A table of results from the lab is okay for record keeping, but having the results on a floor plan is extremely helpful and informative. In making the diagram, it is helpful to highlight those areas that have levels in excess of the EPA action level of 4 picocuries per liter. After you have a map of the results, look for areas that may have a cluster of high radon readings. Perhaps there is one wing of a building that is elevated and other wings are not. This can point you in a particular direction for an initial response. Also, when comparing results, recognize that a tenth of a picocurie difference is not significant, but a difference of one or more picocuries does represent a difference when making comparisons. Here's an example where a central pod area was higher than all the other pods. Why? It was determined that each pod had its own individual air handler, and the fresh air makeup to the one that was serving the central pod was closed. A simple repair of that damper fixed the issue. Here's an example where all rooms in the school are less than 4 picocuries except 2 adjacent rooms. Why? Well, partition walls had been added that separated the supply air from the return. A simple work order adding ducts to both sides of the 2 rooms dropped the radon levels to well below the action level, similar to the results in the rest of the school. If an HVAC issue is not obvious and there's an energy management system in the building, it would be prudent to have a radon professional deploy a continuous radon monitor in one or more rooms that have demonstrated high radon levels. By doing so, you can determine what the actual radon exposures are during occupied hours. You may learn that your HVAC system is already fixing the problem, or maybe you need to set the timers for the controls to come on a little earlier or shut off a little later, depending upon when students and staff are present, including janitorial staff. The thing to keep in mind when doing this is that the original devices that were used to initially identify a radon concern provided an overall average for the 2 to 3 days they were deployed, including radon levels at night. Whereas the results of the continuous radon monitor will allow one to separate occupied versus unoccupied radon exposures. More often than not, a bit of detective work will identify a problem that can easily be fixed. Start with verifying outdoor air makeup is being provided and at the right time. Coils are clean, filters are in good condition, clocks that control when fresh air is provided are set correctly. Sometimes this may mean even getting inside the air handler and verifying the dampers are truly open. Use a smoke bottle or measure the airflow directly. Verify ductwork is balanced and no supply air is being blocked or isolated. Seal penetrations around utility lines under unit ventilators. But don't just assume these simple repairs are sufficient. Repeat radon tests to verify levels have dropped well below the 4 picocurie per liter action level. So what if you have reviewed and fixed glaring problems with your HVAC system and the radon levels are still elevated? Don't think that was a wasted effort, because if not only has it improved the air quality and comfort, it also made the application of another approach called active soil depressurization to be more effective. Active soil depressurization, or ASD, is a method for reducing radon entry by creating a vacuum under a building's foundation that is greater in strength than the vacuum applied to the soil by the building itself, and preferentially collects the radon before it gets into the building and exhausts it to a safe location outdoors where it will not re-enter the structure. By reducing the internal vacuum within the building via HVAC system repairs, the ASD system does not have to work so hard since the interior vacuums have been reduced. Let's take a look at how ASD works. For a slab foundation, a hole is cored through the slab at a strategic location. A couple buckets of dirt are hand excavated. A PVC pipe, typically 4 inches in diameter and not sheet metal, is connected to the hole and routed to a fan located outside the building envelope, with its exhaust point located above the roof and at least 10 feet from a building opening and 25 feet from a mechanical intake. After all, you wouldn't want to go to all that work and allow the exhausted radon to come back into the school. Since radon is continuously being produced in the subgrade, the fan must be a radon fan which is rated to also run continuously. It should be installed in a vertical orientation with piping slope back to the suction point, since soil moisture will condense inside the pipe. and you wouldn't want it to accumulate in any traps or low spots, causing the radon system to stop working. When operational, the fan will draw radon laterally under the slab and exhaust it to the outdoors. The effect of these systems can be seen very quickly after they are turned on, since they are collecting the radon where it's at its highest concentration and before it has a chance to enter the building. However, the area impacted by one of these systems can be limited by the presence of footings that can block this lateral airflow beneath the slab. This is especially true in schools where classrooms are often separated from each other by footings. There can also be footings on either side of a hallway separating classrooms that will limit the area that can be treated. As you can imagine, the presence of footings isolating multiple rooms can lead to a significant number of individual systems in a school where many classrooms may need to be treated. But a properly trained and experienced radon professional can find ways to reduce the number of ASD systems. Sometimes the suction points can be strategically placed near utility lines under a slab, penetrating several footings. The loose bedding or settling around a utility line can provide a pathway for the radon system to impact multiple rooms. Another trick is to install the pit from the outside through the foundation wall just below the bottom of the slab. This has the advantage of not having the system being inside the classroom. It can also allow the installation of suction points on either side of the footing that separates adjacent classrooms, and hence treating two rooms with the same system. Determining the number of systems is not based upon the square footage per system. The porosity of the soil and the pathways between different areas is what determines the number of systems you'll need. Unless, of course, you want one at every classroom, which is both expensive to install and more expensive to operate and maintain. The better way of determining the number and impact area of an active soil depressurization system is to conduct field diagnostics where a soil depressurization system is simulated. Conducting slab diagnostics is as much of an art as it is a science and requires experience. School personnel are advised to contract with a radon professional to conduct diagnostics and utilize the data obtained from the exercise to then develop a scope of work for radon professionals to bid upon. Let's take a look at how slab diagnostics are performed. A preferred location for a potential suction point is selected, and presumably a location that will not interfere with room use. This is typically near a wall which is out of the way, but also near a footing where there has been some settling causing a void under the slab, which can be a benefit. We may also be near, but not on top of, sub-slab plumbing lines, but not in the center of the slab, as that may be intuitive to some. For a number of reasons, locating a suction point in the center of the slab is a bad idea. An 1¼ to 2 inch hole is drilled at the selected suction point, taking care not to damage underslab utilities. Smaller 3/8 inch holes are drilled at different locations on the slab. This would be done on the slab of the subject room as well as slabs of adjacent rooms if they are also being treated because they have elevated radon levels. A micromanometer is then attached to the smaller holes with one port connected to a tube inserted into the hole and sealed with putty, and the other port open to the room air. This will allow one to measure the pressure difference across the slab at these test hole locations. The suction side of a large shop vac is then connected to the larger hole that was drilled through the slab at the proposed suction point. Pressure differentials are made at each pilot hole when the vacuum cleaner is turned on. A demonstrable change in vacuum will indicate that a fully installed system will be able to extract radon from that location of the test hole all the way back to the suction hole. If communication is found to occur on opposite sides of a foundation wall, even better, because that means that the system will, when installed, can treat more than one room. Pressure measurements from the pitot tube pilot holes, as well as airflow measurements, allow the radon professional to select proper fan and pipe sizes. It would provide the design basis and scope of work for obtaining proposals for repair. A companion video of a case study of a school in North Dakota has been developed which demonstrates slab diagnostics as well as how the building's HVAC system was reviewed and recommendations developed. You may not have a slab, but rather a crawl space under the building or a portion of it. Crawl spaces are notorious for allowing a lot of radon into classrooms above them due to the large amount of earth exposed, even if there are crawl space vents. One approach, referred to as submembrane depressurization, is very similar to how we treat slabs. In fact, the same type of radon fan and piping system is used. What is different is a durable polyethylene sheet is laid on the earthen floor and sealed to foundation walls, with additional sealing at seams and columns or piping penetrations. This provides a quasi-barrier similar to a concrete slab. A length of perforated pipe is installed beneath the sheeting connected to the radon system. When activated, the radon is captured in the space between the crawlspace floor and the sheeting. This is very effective in reducing radon within the crawlspace and hence the occupied space above. On the other hand, it can involve a lot of poly sheeting and a lot of caulking and sealing. The good thing is that it's not essential to perfectly seal all gaps in the poly. In fact, it is impossible. Seal where you can, and where you can, air will be pulled down through the gap rather than allowing radon-laden soil gas to pass upwards into the crawlspace. Another approach that can be considered for crawlspaces is where the floor above the crawlspace can be readily accessed from either above or from within the crawlspace. In this approach, the floor becomes the critical barrier rather than an installed membrane. A fan is used to pull air out from the crawlspace, creating a negative pressure in the crawlspace. This causes air from the room above to go down into the crawlspace rather than radon-laden air coming up into the room. To reduce the loss of conditioned air, efforts should be taken to seal openings in the floor assembly with expanding foam or other sealants compatible with the floor. This is typically done from within the crawlspace. However, in the case of very low clearances that may be found in older schools, the sealing will need to be done from above. The fans should be variable speed or dampers be installed in the ductwork to reduce the amount of air that is withdrawn to be just enough to create a negative pressure within the crawlspace relative to the occupied space above. A few additional things to consider when applying this method, referred to as crawlspace depressurization, is it is more effective to pull air out of the crawlspace rather than blowing cold outdoor in, which can freeze pipes. The radon level within the crawlspace will increase, and future access to the crawlspace for maintenance may require temporary ventilation for workers. And also, the discharge of the radon system should be routed up above the roof and away from openings, as was the case when installing a slab system. Another way active soil depressurization can be applied is if there is a surface water collection system for the building, such as a sump or a perimeter drain. Since water from the subgrade enters these systems, a vacuum applied to either a sump lid or drain piping connected to it will also serve to collect radon, even if the perimeter drain is outside the foundation. This is one of the many skills that a radon professional can draw upon, but care should be taken that the surface water collection system is not compromised and sump lids are well sealed, yet accessible for pump repair. So as you can see, when addressing a radon concern in a school, there are several steps that can be taken in a logical sequence. First, verify the measurements have been done properly. Follow up with hourly measurements to determine actual exposures to students and staff. Assess the HVAC system for deficiencies of fresh air makeup and balancing. Verify reductions, and if HVAC systems are not sufficient to reduce radon levels, engage a radon professional to develop a design for the installation of an active soil depressurization system. Then implement the design. But always retest the school to verify reductions. And then implement a management maintenance plan. As far as management plans are concerned, it is important to realize that even though the survey you are responding to may have shown specific rooms that were elevated and others that were not, the ones that are currently not elevated could become elevated in the future if the HVAC systems for those areas change. After all, the soil under the entire building has the same radon potential, and the only reason it may not be entering a given room now, it could in the future. If, for example, a supply duct is closed, or the fresh air makeup for the unit servicing that area is closed, or the filter is not changed. So what this means is that a proper management plan should address all rooms within the school, as the potential for elevated radon exists throughout the building, and vigilance regarding HVAC maintenance and repair is a necessity, and retesting of the entire facility every year. Hopefully this video will provide you a basis for addressing elevated radon in your school. Every building is a little different, and some are easier than others. But recognize that radon is definitely fixable, and if you have elevated levels, it should not cause a panic. And as you have learned, many of the repairs can be addressed by in-house maintenance staff. If the repairs are more complicated, a radon professional can certainly assist. However, if you do contract with a radon professional, verify that they are certified and trained for treating large buildings. And it is best if the radon professional works in conjunction with maintenance staff and the HVAC contractor that services your building. A team approach works well, as there are many aspects of a building to consider when approaching radon reduction. Associated with this video is a case study of a school in North Dakota that had elevated radon levels. In it, you will see the analytical steps that were taken in identifying why radon was a concern and the steps recommended for remediation. And in closing, if you have any questions, do not hesitate to contact your state radon contact or myself at CERDI. Thank you.